Today's a huge day. The reason today's a huge day is because one of the central themes in our trig class has been that of solving triangles. In fact, let me just remind you the world of trig. In the world of trig, you got some major topics. You've got solving of triangles, which we've done part of. If you recall, the first couple of weeks of the course, we did solving right triangles. The ones we didn't solve are the ones that are not right triangles. That's why today is a huge day, because today we get to finish this topic. Other topics were the functions. We've been getting to know the functions over the last few chapters. Gotten to know the definition, their graphs. Huge topic was the identities. Just lately we did solving equations, and that puts us where we're at now to finish this first central theme here, solving triangles. Today we get to solve non-right triangles. Non-right, which means they may not have a 90-degree angle. That's why today's a huge topic. Not only that, but once we complete this section or this chapter, today we're doing the law of cosines. Next lecture we'll do the law of sines. Once we complete these two sections, that's it. This would be what most people would consider a well-founded first introductory course to trigonometry. That's got all the essential things. The next chapter is just a little bit some miscellaneous topics, which, don't get me wrong, they're huge topics too, and they're beautiful too. But it's not usually what people would call trig per se. It's more of some miscellaneous topics that are usually taught with the trig course. Okay, so let me tell you the situation. The situation goes like this. If we have a right triangle, for example, this one, and we have three items given. One of the angles, and say one of the sides, and say another one of the angles. Say this is I don't know, 20 degrees. Then it's all over, because from here we can figure out the rest. We figure out the tangent or the sine. That tells us the ratios here. We figure out the cosines. That tells us the ratios here. And this will be easy to do. We've done this before. Solving right triangles is something that's in the bag already. Done. The situation is like this. Now we want to attempt, or we want to learn how to solve triangles that may not be right triangles. So for example, take a triangle like this one. This one may be absolutely not a right triangle, and so the question is, can we do it again here where three items are given? For example, suppose I give you that this is 10 degrees, and suppose I give you that this is 15 units, and suppose I give you that this is 5 units. That alone, three items are given. Count them, three. Same as before, three items were given. Can you figure out the other three items? Remember, triangles have three angles, three sides. The name of the game is usually, the situation goes like this. They give you three items are given, or known, and the goal is to find the other three. That's what we call solving the triangle. That's the situation. The tool, what are we going to use to do that? Well, the perfect tool is, the perfect medicine is, of course, what do you suppose the perfect medicine is? The perfect medicine for that is exactly the law of cosines. With the law of cosines, we'll take care of these triangles. No problem. We'll just give it some law of cosines. It'll be done. So then that leads us to a couple really important discussions. First, what does the law of cosines say? Second, how do we actually go about using it? And third, we want to own it. Where did it come from? How do we prove it? How do we really make it ours? Any old chump can memorize this and use it. Even a dolphin could probably use it. But it's a rare human privilege to be able to understand things. That's what we're going to end up with today. So that's the game plan. Okay? Recap. Huge day today. Today we finished this important theme here, solving triangles. We had already started it before for right triangles. Today we finish it for non-right triangles. And not only that, but in this section we complete what most people regard as a general trig course. Okay, the situation, we already know the right triangles, we want to know the non-right triangles. The medicine, the law of cosines. Okay, enough talk. Let's actually do it. What does the law of cosines say? Well, here, remember, this is a good way to understand what the law of cosines says. Do you remember the Pythagoras theorem? If you don't, let me remind you. The Pythagoras theorem said, so long as you have a right triangle like this in flatland, in Euclidean space, then we have this very, very special relationship between the sides of the triangles. The relationship goes like this. A squared plus B squared, the squares of the sides added together give you the same amount as the square of the hypotenuse. That's super, super famous. Anybody who is somebody knows that. That's the Pythagoras or Pythagorean theorem. Depends if you're English or not. All right. Super, super famous Pythagorean theorem. And then the question is, how is this related to what we have to study today, which is the law of cosines. The law of cosines is, in fact, intimately related to the Pythagorean theorem. Here's one way to think about it. One way to think about it is, suppose that, well, one way to think about it is like this. Right here, this is the Pythagorean theorem. An old shoe. You can think about it that way. There's no judgment, by the way. I got nothing against old shoes. For sure, they've served their purpose. You can think about this as the Pythagorean theorem, and the way you can think about the law of cosines is a brand new shoe like this. The law of cosines. So it's a brand new and improved version of the Pythagorean theorem. And let me explain further why I think that's a great analogy. Here's why I think about that's a great analogy. Because the Pythagorean theorem tells you how sides of the triangle are related. Well, not all triangles. This one only limits itself to right triangles. If you have a right triangle and you have A, B, C, the Pythagorean theorem says, hey, A squared plus B squared is equal to C squared. Law of cosines takes that up to the 21st century, says, hey, I got something better on that. The law of cosines says, I don't even care if it's a right triangle, and this is a great, great, great breakthrough, that this one applies to any Euclidean triangle, okay, in flatland. This one says, as long as you tell me, well, this one says, look, if I'm standing here, on this side right here, and I call these sides A, B, C, then the law of cosines would say B squared is equal to C squared plus A squared. So it assumes that you're standing at the right triangle, or at the right angle, and it almost acts like Pythagorean theorem, where it pretends that across from it is a hypotenuse, quote unquote, because it may not be if this is not 90 degrees. But so far it looks a lot like the Pythagorean theorem. It says B squared is equal to C squared plus A squared. But then it reflects on itself and says, hey, wait a minute, that may not be true if this is not a 90-degree angle. In fact, if this is any angle, let's just call the angle capital B, since it's across from B, it says, you know what, this may not be right. So to compensate, I know exactly what the error is. The error is you have to subtract 2 times these two, C times A times the cosine of B. And that is exactly what the law of cosine says. Get it? Here, let me take that and explain it a couple different ways. The law of cosines discriminates against none of the sides. It has no discrimination. It says, I don't care which one of you is the hypotenuse. In fact, it says, you're probably neither one of you, none of you are the hypotenuse, because this is probably not a right triangle. And if it is, I don't care. I could apply Pythagoras from any quote-unquote Pythagorean theorem from any corner. watch this. You could stand on this corner, and the law of cosines would say, from this corner, it looks like c squared is equal to a squared plus b squared. That's what Pythagoras would say. But the law of cosines says, I know this is wrong if this is not a right triangle. Let me write that. C squared is equal to a squared plus b squared. It says, I know that may be wrong, so I know how to fix it. You subtract 2 times these guys, 2 times these two, 2 times AB times cosine of the angle here where I'm standing. You see? So it could be applied from here. It could be applied from here. From here, it'll say, I'll treat that guy across from it. I'll treat him I'll treat him or her as a hypotenuse, and I'll say that b squared is equal to c squared plus a squared. And that's where it would stop if it was a right triangle. But the law of cosines is conscious that, hey, it may not be a right triangle, so to compensate for that, you subtract the error, which is always twice times CA times cosine of the angle between them, B. It could even be applied from this corner. I'm telling you, the law of cosines discriminates against no side. From this corner over here, it says I can treat the one opposite. I can treat the A as a quote-unquote hypotenuse. It'll just look like this. A squared is equal to c squared plus b squared. Again, whoa. Come to daddy. This thing is not moving. Easy. Told you. Alright, if it was a right triangle, that's where it would end, but the law of cosine says it may not be a right triangle, so I know how to fix it. I'll just subtract twice CB times the cosine of the angle where in the corner I'm standing. That right there, that's the law of cosines. Okay? Apply from any different side of the triangle, and so in many sense, this is the perfect analogy. The Pythagorean theorem was nice. It's like an old shoe. It's dependable, but it has its limitations. It lived its purpose when we were limited to the world of right triangles. If we increase our world to non-right triangles, then we need something brand new and shiny. We need the law of cosines, which generalizes the Pythagorean theorem. Okay? Incidentally, you can't really say this is better because, as you will see when we actually prove it, to see where this comes from, guess where this one comes from? It comes exactly from the Pythagorean theorem. So, without the old shoe, the new shoe is nothing. Just a little one. So you should appreciate both your shoes. Okay? Now let's say a couple things about the method. How do you take this perfect medicine to solve these triangles? You should be a little bit cautious because depending on where you apply it, you may get different results. As we just explained, the law of cosines can be applied from any one of the 3 corners on the right triangle. And the results will be different depending on which corner you decide to apply it at. So let me just say a little bit on that as far as the method goes. One of the crucial things that will play a role here will be the number of unknown quantities. Let me give you an examples, okay? An example. Suppose that you've got 3x plus 2 is equal to 10. That's an equation, and you can go on and count how many variables have you got, how many unknown quantities. And if you see there's only one unknown quantity, that's generally a good thing. If you don't believe me, compare it to this. 3x plus 2y plus 4z is equal to 10. Suppose you had to solve that for the unknowns. You have 3 unknowns, x, y, and z. In fact, this is a much longer story. You may recall from your algebra class you would have to construct a system of equations. It may turn out to be a dependent system. You may have to do Kramer's rule. It's kind of a longer story, and so if you had to choose between these two, solving just one variable and solving a lot, you should understand that in some sense this is much more desirable. Okay, you can solve x more directly here than you could over here. Okay, assuming that you like solving things directly, you would probably prefer this one. One variable, not 3, not 2, not 5, not 7. The preferred scenario is one equation, one variable. one variable. Okay, if you have to, sometimes you got no choice. You need to solve equations that have many variables, and that's okay. That's the way life goes. Those could be fun too. But this may be a more direct route to solve our equations. So make a distinction here. Now, when you apply the law of cosines, let's count the law of cosines. All right. So if you apply it from this corner, how many unknown variables do you have? You have b, c, a. The 2 is known. 2 is just a constant. The c, the a, and the angle b. In total, there are four unknown quantities here. And I can make a little diagram here of the quantities involved. This one involves the b and the b. See, the b is in the equation, and so is the little b. The b angle and the little b. And it also involves these two, right? The c and the a. Those are the 4 quantities that are involved. If you knew 3 of them, you could write this equation and you'd have 1 unknown. On the other hand, if you stand on this corner, these are the variables that are involved. Those 4 variables, the c, the 2 c's, and the a and the b. It would be a good idea to apply it from this corner if 3 of those are already known, so that you can just solve for the unknown part. Does that make sense? It's just basically a way of looking at this. Hey, if you like, if you want to solve for something, a more direct way of doing it may be to write down an equation that only has 1 unknown. Okay, let's actually do that in real life here. So let's call this one A. So this will be, I shall call this little a. I shall call this big C, and I'll call this big A. So think about it. If I stand over here and I apply the law of cosines, I will get that, I will treat this one as a hypotenuse, so I'll get that 5 squared is equal to a squared plus 15 squared. And that would be as far as Pythagoras takes you, but the law of cosine says, hey, I know exactly what the error is. You have to subtract 2 times a times 15 times cosine of c. And you counted this. Now look at this equation. Focus all your might and all your attention in this equation and count. How many unknown quantities have you got here? The a is unknown, the a is unknown, and the capital C is unknown, the angle. So which one of these equations is this? The one that has many variables or the one that has just one variable? Obviously this is the one that has more than one variable. So if you got no other choice, if you got nothing else going on, that might be a way to start. But think about the difference that it would make if you stood on this side instead. If you stand on this side, which variables are going to be involved? Just think about it. These 2 are going to be involved, and these 2 quantities will be involved, and those 2 quantities will be involved. You got 4 quantities. How many of these 4 do you know? Do you know the 5? Yes. Do you know the 15? Yes. Do you know the 10 degrees? Yes. Do you know the a? Yes. No. You don't know the a. You know 3 of them, and you only have 1 variable. So this would be a more direct way to solve it, because you'd write it like this. You'd say a squared is equal to 5 squared plus 15 squared. All right, that's as far as Pythagoras would take you. And law of cosine says, wait a minute, you got to subtract 2 times the 5 times the 15 times the cosine of 10 degrees. And you scan through this equation, and how many unknown quantities do you see there? Of course, you only see the a is the only unknown quantity. So out of these 2 equations, both of them are consistent. Both of them are correct applications of the law of cosines. They're both legal, but they're not both as helpful. You guys understand? This one is not as helpful because you've got 2 unknown quantities. This one is really helpful because immediately you can solve for a squared. In fact, let's do it. Why not? I'm not afraid. Let's solve for a squared here. So you have that. In fact, let me copy this equation here. Let's do a little copy. We'll paste it over here. There it is. So to solve for it, we would just go like this. A squared is equal to 5 times 5 is 25. And then 15 times 15, that is... Okay, so let me bring out my little magic number machine. 15 times 15 is 225. So this will be 225. Minus 2 times 5 is 10. That's 150. times cosine of 10 degrees. So that gives me that a squared is equal to 250 minus 150 times cosine of 10 degrees. That gives me that a squared is 250 minus, I'm going to take this again on my little magic number machine. Where are you, little number magic machine? Whoa, whoa, whoa. You guys all right there? Let me see. The little magic number machine will try. Let's see. We got to do 150 times cosine of 10 degrees, and we get an approximate answer. That's approximately 147. I'll just leave it like that. You shouldn't round off so much, but just for our purposes, I'll just keep it to 2 decimal spots. Alright, so that means that a squared is equal to 102.28, and so a is equal to plus or minus the square root of 102.28. Now, if we assume that that a is the side of a triangle, and we assume that it's positive, then we'll have to go with the positive ratio. So a is approximately the square root of 102 point whatever it was, 28, I think. Okay, and that's exactly the method that you generally use to solve non-right triangles using the world famous law of cosines. Super famous, huh? In fact, on this triangle, we're not even done yet. You solve for a, you solve for the two sides. Now you need to solve for the angles. And again, that requires a careful thought here, but it's no problem. You could apply it now from this corner, because look, if you applied the law of cosines from this corner, let me think. Let's delete this, and let's delete this. From this corner right here, the quantities that are involved would be these two quantities and these two quantities from this corner. And count, how many unknowns do you have? The c is unknown, that is known, that is known, and that is known. So if playing from here would leave you with just one unknown variable, this would be successful. This would be a successful application of the law of cosines if we just finish it. Let's do it. So in fact, I'll actually copy this, and I'll just remember that a is equal to the square root of 102. So I'll go over here, and I'll paste it. And now we have to solve that. And keep in mind that we know what a is. A is the square root of 102. So then this becomes 25 is equal to 102.28 plus 15 squared. We said it was 225 minus 2 times the square root of 102.28. I'm just substituting all the a's in there. Times 15 times cosine of c. Right? And let me think. We can clean that up. This will be 25 is equal to, I can combine these two. That would be 327.28 minus, this would be 30 times square root of that. So let's bring out the little number magic machine. So I'm going to do, hold on, Diego. Yeah, you could borrow these. So this would be the little number magic machine. I need to do 2 times that square root times 15. So I'll do 2 times the square root of 102.28 times 15. And that is approximately 303.4. So this would be 303.4 times cosine of c. Capiche? Now I can swing this over to the other side. This goes over to the other side, and that will give me, see, notice, count number of unknown quantities. How many unknown quantities do you have? Everything is known, known, known. The only unknown quantity is, of course, the c, which is good. We like equations that have just one variable, one unknown quantity. Alright, so I subtracted 327. So I bring out my number machine. I go 25 minus 327.28. What does that equal to? That's negative 302.28. So it should be negative, not with a magical disappearing ink, negative 302.28, and that's equal to negative 303.4 cosine C, right? And then we want to subtract both sides by, or not subtract, divide both sides by, we'll divide the left side by negative 303.4 and divide that side by negative 303.4, and that will give us cosine C is equal to 302.28 over 303.4, or said differently. By the way, all these are approximations, because once I approximated this stuff, forget it. It wasn't really equal, even though sometimes I forget to mention it. These are all approximations. And so now I have that cosine C is approximately equal to, I need to divide these, 302 divided by negative 303.4. And that would become 0.996 approximately. So this will be 0.996 approximately. Now, what kind of equation do you have? You have basic trig equations, the kind of equation that we learned just a couple sections ago. And so this part is really crucial. You should always solve these correctly and honestly, just like we learn how to solve them. Okay? More on that in just a second. Okay, now let me remind you, the way we solve these is we make a small little graph. We try to graph one of the equations, cosine. The cosine equation goes like this. This is famous. This is the way it goes. That's a little bit more than a period, and then 0.96. 0.96 would be more or less here. 0.96 is a little bit less than 1, something like that. The solutions, the angles that we're looking for, are these angles. They occur here, here, here. There are infinite many solutions to this equation. The first one we obtain by using the calculator, because this is not a famous ratio. We can do it using the calculator, so we do something like this. Shift cosine of 0.996, and that should give us approximately 5.12 degrees. So this one right here is approximately 5.12 degrees. Using that in the symmetry, you should be able to find out the other ones. The other one is 360, take away 5, so it'd be about 355. 354.88, and so on and so forth, degrees. Now keep in mind that we're trying to figure out the angle C, and the angle C is an interior angle here. We're trying to figure out this angle C. Now, so far we have choices like C is equal to 5 degrees, 5.12 degrees, 354.88 degrees, 365.12 degrees, going on the left side, negative 0.5, negative 5.12 degrees, etc., etc. Of all the possible candidates, these are all candidates. We have to keep in mind that this is the interior angle of a triangle. So if we can assume that these guys add up to 180, then it couldn't be these angles, any of these. And if we can also assume it's a positive, there's only one choice from the candidates. The only choice is, of course, 5 degrees. This is a very careful analysis, because there will actually be times when two of the choices are possible, and the possibilities will be more than one triangle. So I can't emphasize how important it is for you to solve the equations correctly and look at all the possibilities and do not discard them until you have a good reason for it. For example, I have a good reason for discarding this one because it's more than 180. It couldn't possibly be one of the interior angles. And we assume that it's positive, so it couldn't be any of the negative ones. So it leaves you with one choice. C is 5.12 degrees. That's the end of the story for C. It's nice, huh? And of course, and A is really easy because these two have to add up to, all these three have to add up to 180. So if these two add up to 15 degrees, roughly speaking, then this one has to add up to 165, more or less. Approximately 165 degrees. So that they can add up. It's actually 164.88, but whatever. And there you go. We did it. We solved the triangle. We solved it carefully. We used the equations. We used law of cosines. We paid attention to which application of the law of cosines was better, depending on which corner we stand. Every time you stand at a corner, you got involved 4 variables. You count which of the 4 variables are known, so that you only have one unknown. Okay. Very, very nice.